Hello students, today we shall see more examples on test of consistency and solution of a system of linear equations, and also we shall see matrix inversion by Gauss-Jordan method. So first let us see examples. Investigate for what values of lambda and mu the following system of equations has a unique solution, infinitely many solutions, and no solution. Three types of solutions rather two types of solutions, and third one is no solution, means inconsistent. For what values of lambda and mu this system is given here. So first we shall write this system in matrix form. So coefficient matrix here is 1 minus 1 2 first row, second row 3 minus 2 9, third row 2 minus 4 lambda written, and then capital X means here small x y z variable vector, and right side is 4 14 mu written. We write it as Ax equal to B, say coefficient matrix A, and B is right side column vector. Now we shall write the augmented matrix, third bracket A colon B. The right side column vector B, when attached here, it will become augmented matrix. So it is written here. Now we shall convert this augmented matrix to echelon form. The element in the first and first column is already 1, so it's better. If it is not 1, we shall make it 1, but here it is already 1. So to convert it to echelon form, first we do the operation second row minus 3 times first row, third row minus 2 times first row, so that these two elements below 1 are 0, means x eliminated from the system. Okay, so it is symbolized as R2 changed to R2 minus 3R1, R3 changed to R3 minus 2R1. So accordingly we have calculated here. So again the first non-zero entry in the second row is 1, so it will be easy to make this element 0, so that the matrix becomes in echelon form with the help of this. So it will be third row changed to third row plus 2 times second row, so R3 changed to R3 plus 2 R2 we have written. So it is 0, and lambda minus 4 when added with 6 it will be lambda plus 2 written, and mu minus 8 when added with 4 it will be mu minus 4. Now we see that zeros are in increasing trend, and this augmented matrix is in echelon form, so which is in echelon form. Now we shall investigate for what values of lambda and mu this system has a unique solution, this system has infinitely many solutions, this system has no solution. So first we shall see for unique solution. For unique solution, we know coefficient of augmented matrix and coefficient of rank of augmented matrix and rank of coefficient matrix should be equal, and that should be equal to the number of variables, number of unknowns. So there are 3 unknowns, 3 variables, so rank should be 3. Now if lambda plus 2 not 0, lambda plus 2 not 0, then third row is non-zero. Whether mu equal to 4 or not, no matter. If lambda plus 2 is not 0, then third row will be non-zero for both A and A colon B. Up to this is A. So if lambda plus 2 not 0, rank A will be 3, and automatically rank A colon B will be 3, because this is non-zero. So that's why we have written if lambda plus 2 not 0, that is lambda not equal to minus 2. Then for any value of mu, whether mu is 4 or any other real value, we see that rank A is 3, rank A colon B means rank of the augmented matrix is also 3. And that 3 means it is equal to number of unknowns or number of variables. Therefore the system in this case is consistent and has a unique solution for any real value of lambda and mu except lambda equal to minus 2. So this is our first investigation. Next, for many solutions, infinitely many solutions, if lambda equal to minus 2, this will be 0, and mu equal to 4, then also this will be 0, means fourth row will be 0. Lambda equal to minus 2, mu equal to 4. In that case, for both A and A colon B, fourth row will be 0, means rank will be 2 for both of them. So that's why we have written if lambda equal to minus 2 and mu equal to 4, we see that rank A equal to rank A colon B, means rank of the coefficient matrix and rank of the augmented matrix are both 2, and that is less than number of unknowns, number of variables, and therefore in this case the system is consistent and has infinitely many solutions. because there will be 2 equations and 3 unknowns. That's why infinitely many solutions. Then we go for no solution. If lambda equal to -2, this will be 0, means rank of the coefficient matrix will be A will be 2, and if mu not equal to 4, then rank of the augmented matrix will be 3. Rank of the coefficient matrix 2 and rank of the augmented matrix 3 if lambda equal to -2, mu not equal to 4. So that is written here. If lambda equal to -2 and mu not equal to 4, then we say that rank A equal to 2 and rank A colon B means augmented matrix is equal to 3. So that rank A not equal to rank of the augmented matrix, and hence the system is inconsistent. That is, the system has no solution if lambda equal to -2 and mu is any real number except 4. Okay, so this was the question investigation. You can see that if lambda equal to -2, these 3 elements will be 0 and mu not equal to 4. In that case, if you want to write the third changed equation, it will be 0x plus 0y plus 0z equal to non-zero number, because mu not equal to 4. So 0 equal to non-zero. That is absurd. That's why we said that the system is inconsistent in the third case, and that is, the system has no solution. Next example. A student wrongly copied a consistent system of 3 linear equations as follows. Student wrongly copied. These are the equations given. On checking, it is found that the constant term in the third equation, means this 3 constant term in the third equation, was wrongly copied. While other parts are correct, means all other entries are correct. Only this 3 is wrong. Determine the correct form of the system of the linear equations and solve it. Means what this 3 is to be replaced by what, so that it becomes consistent and also to solve, because already it was consistent. So in matrix form, the given system of wrongly copied linear equations is, we have written 1 2 1 first row, coefficient matrix 2 1 1 second row, and here x is absent, means 0 5 -1 we shall write 0 5 -1 xyz, and right side is 1 1 3, that is wrongly copied. So this is system in matrix form, or you can write Ax equal to B. Say this is A, this is X, this is B. Augmented matrix of the system is third bracket A colon B is this. This is capital A, this 1 1 3 attached here. So we have got augmented matrix. Now we shall convert it to echelon form. Already there is a 0 in the third row, first element. So we shall make this 2 0. So second row -2 times first row. So R2 -2 R1. We have made this applied this elementary row operation. So 2 zeros are here. Now to convert it to echelon form, we need this 5 to be made 0. So third row minus second row gives us 0 0 and 4. Incidentally, this is also 0. Now this is in echelon form, which is in echelon form with 2 non-zero rows for A. See, this up to this was A. So 2 non-zero rows for A and 3 non-zero rows for A colon B, augmented matrix. Therefore, rank A equal to 2 and rank A colon B means rank of the augmented matrix is equal to 3. Therefore, rank A not equal to rank of the augmented matrix. Therefore, the system is inconsistent, but in the question it was written that it was consistent system. Therefore, wrongly copied system is inconsistent, whereas the original system was consistent. So we must have rank of the augmented matrix also 2, because other entries in the augmented matrix are correct except the element in the third row and fourth column of it. In the augmented matrix, this entry is wrong as written in the question. Okay, only this entry is wrong, so we have to rectify it. We have to change it to make it consistent. So what is to be taken instead of 3? Therefore, wrongly copied constant term 3 of the third equation of the system must be actually what? -1. Why? See, this 3, if it is -1, it will remain here also -1, and in that case -1 -1. Here we have applied the operation R3 minus R2. So -1 -1 will give us 0. So our wrongly copied constant term 3 of the third equation of the system must be actually -1, so that in that case rank A and rank of the augmented matrix will be both 2 equal and the system is consistent. Therefore correct form of the system of equations is first equation, second equation as it is written, only third equation we have written 5y minus z equal to -1. This is the correction. It was 3, now it is -1. So we have corrected the wrongly copied system and thus the system becomes consistent. But in that case rank of A and rank of augmented matrix will be 2, means infinitely many solutions will be there. So after correction, in this case the augmented matrix in echelon form is here, it will be 0. This 4 will be now 0, other things remaining same. So we have written it 1 minus 2 1 1, 0 5 minus 1 minus 1 and 0 0 0 0. Okay, so this is augmented matrix AB, but not equal we have written because equivalent. After elementary operation application it remains equivalent so far as rank is concerned. Therefore reduced equivalence correct form of the system is, why reduced? Because you see the third equation is eliminated, all 0, 0x plus 0y plus 0z equal to 0, no problem, it is eliminated. So reduced equivalent system, from 3 equations we have got now 2 equations. So x minus 2y plus z equal to 1 and 0x means plus 5y minus z equal to -1. So we have written 5y minus z equal to -1. Now from these 2 equations we have to find the value of 3 variables. Surely there will be infinite number of solutions. Geometrically also we can explain it like that. This is equation of a plane, this is also equation of a plane, and 2 planes intersect along a straight line, and on a straight line there are infinite number of points, that's why there are infinite number of solutions. So from this to z equal to 5y plus 1, now putting this value of z here, we get x equal to 2y minus z plus 1 means 2y minus 5y plus minus 1 plus 1, so minus 3y. Therefore solution is given by x equal to minus 3y, we have written here 3k, and y equal to k, we have assumed y equal to k, and z equal to 5y plus 1 means 5k plus 1. What is k? K is any real number, so k has infinite number of values, that's why the system has infinite number of values. But the system has infinitely many solutions, but only n minus r plus 1, it is a non-homogeneous system. So n minus r plus 1 means here n means number of variables, 3 minus rank is here 2, plus 1 equal to 2 numbers of the solutions are alike. So only 2 of the solutions, there are infinite number of solutions but 2 solutions are alike. The system is only 2 alike solutions, 2 linearly independent solutions, and all others will be linear combination of these solutions. Okay, example number 4. Solve the following system of equations by Gauss-Jordan method. Gauss-Jordan method was explained in the last lecture. Now only problem we shall do. Gauss-Jordan method. 2 problems, one I shall do here and next one you will do. Answers are given for second one. So first one. In this case, number of equations equal to number of variables here. In matrix form, the given system is 1 1 1, 2 minus 3 4, 3 4 5 written, and x y z variables 9 13 40. Okay, so ax equal to b. Say the augmented matrix of the system is this a and this 9 13 40 attached here. So you have got this augmented matrix. Now we shall apply elementary row operations only and convert this coefficient matrix. This is coefficient matrix and this is b attached, that's why it is augmented matrix. This coefficient matrix we shall convert to a unit matrix or a diagonal matrix. Better we go to unit matrix, and then readily variables will be obtained. So for that what we do, second row minus 2 times first row, third row minus 3 times first row. So you have got this. Okay, applying R2 change to R2 minus 2 R1, R3 change to R3 minus 3 R1. Accordingly the elements are changed, 2 zeros are there. Then we have to make this element 0, so it will be better if we take this one first in the second row position and this second row in the third row position. So R2 R3 interchanged, means second row and third row we have interchanged. If leading element first non-zero entry is 1, then it is better to make other elements 0, that's why we have done. Now if we interchange, if we add 5 times second row with third row, we shall get this element 0 easily. So that's why R3 change to R3 plus 5 R2. Accordingly it is 12, it is 60. 5 into 13 65 minus 5 added 60. We have got. Now 1 1 1, yes, this 12 let us make 1, no fraction will be coming if we replace third row by 1 by 12 third row, multiplying third row by 1 by 12. So it will be 1, it will be 5. Okay. Now here is a comment. This matrix is in echelon form, and clearly rank A, rank up to this is A, so it is rank A is 3, rank echelon B is also 3, equal to number of variables. Therefore the system has unique solution. So you can find that unique solution here. So after this operation it becomes 1. Now you want to make diagonal 1 1 1 already there, only these 3 elements we want to make 0, so that it becomes a unit matrix. So what is the operation? First row change to first row minus second row, so that this one subtracted from that it will become 0, plus third row R1 minus R2, this will be 0, and R1 minus R2 plus R3, not plus R3, it should be perhaps minus R3, or let us see. 1 minus 1 will be 0, it is 0. Okay, correct. Then 1 minus 2, if we take, it will be minus 1, and then if we add R3, yes, 1 minus 2 is minus 1, and plus 1 it will be again 0, correct. And then 9 minus 13 will be minus 5, minus 4, and then when 5 added it is plus 1. Okay, correct. R1 change to R1 minus R2 plus R3. First row change to first row minus second row plus third row. You have got these two elements 0. Now this is in echelon form, and also this A is a unit matrix. This A part, A has become unit matrix. The coefficient matrix has been reduced to a unit matrix. Therefore solution is readily given: x equal to 1, y equal to 3, z equal to 5. How? Actually, if we want to write this system again, it will be 1x plus 0y plus 0z equal to 1, means x equal to 1. 0x plus 1y plus 0z equal to 3, means y equal to 3. 0x plus 0y plus 1z equal to 5, means z equal to 5. So if coefficient matrix becomes unit matrix, then it is very easy to write the answers directly: x equal to 1, y equal to 3, z equal to 5. That's why Gauss-Jordan method, but it is at the cost of additional calculation, elementary operation. Actually we can solve from this equation, this portion. Up to this if we do, then using Gaussian elimination method, by back substitution we can find x, y, z. So here of course only 2 operations made it a unit matrix, but in some more other problems it may be that up to this, after that there may be 4, 5, 6 steps to make it unit matrix. Okay, so actually Gaussian elimination method is better. Gauss-Jordan method gives readily answer, but at the cost of additional calculations. Okay, second one you will do. Now let us see matrix inversion by Gauss-Jordan method. This we have done in class 12 also, without giving the name Gauss-Jordan method. Here we are naming only it. Let capital A be an invertible matrix, that is a non-singular matrix, square matrix, non-singular, determinant is non-zero, so that inverse exists. We can write A equal to IA, where I is the unit matrix of same order as that of A. Unit matrix IA, you know, diagonally 1, all elements 1, other elements 0s. That is unit matrix. Behaves like 1 in the matrix algebra. Now applying elementary row operations only, this is important, row operations only, because we have written IA, row operations only, we convert A of LHS to I, and accordingly I of RHS in A equal to IA. In this equality, we shall convert A to I, and accordingly I of right side in this A equal to IA will be converted to P is A, that is I equal to PA, so that A inverse equal to P, because PA equal to I means by definition P is the inverse of A. So this is the Gauss-Jordan process method. Why row operations only? Because already we have seen in the last class that if an elementary operation, row operation, is applied to a matrix, or it is pre-multiplied by corresponding elementary matrix, then the effects are same, action same. That's why only row operation, because we have written I to the left. And if we write I to the right, similarly writing A equal to AI and applying column operations only, we can find A inverse. If you right? A is AI. In that case, you have to apply only column operations, because we know applying an elementary column operation to a matrix or post multiplying the matrix by corresponding elementary matrix, the effect is same. That's why. So this is the process for finding inverse by Gauss-Jordan method. Now let us see one example. Find the inverse of the following matrices by Gauss-Jordan method. 1, 2, 3 matrices given. Roman 1 homework, Roman 3 homework, Roman 2 let me do. Let A equal to this. Given matrix, we have named it A. Now we can write A equal to IA. A written here, and what is I? Unit matrix of same order as that of A. A is 3 by 3, so that's why this I will be unit matrix of order 3. Now we shall convert this capital A of left side to unit matrix by using elementary row operations only, and accordingly we shall change only the prefactor of this product IA. Means we shall multiply this capital A, pre-multiply capital A with the corresponding elementary matrix, so effect will be same. So first element should be 1. First column element should be 1. That's what we have done. R1 changed to R1 minus 2 R3. 3 will be 6, 7 minus 6, 1. So that's why we have used this operation. So 6 minus 12 minus 6, 2 minus 16 minus 14. Okay. And then R3 changed to R3 plus 3 R2. So that this 3 becomes 0. After that, after using R3 here, and then we have changed R3, row 3. So row 3 plus 3 times row 2, that will be 0. 6, 6, 12, 12, 8, 20, correct. And same operation we have applied only to the unit matrix here. So R1 minus 2 R3. So this will become 2 R3. This will become minus 2. Okay. And R3 plus 3 R2 means third row plus 3 times R2 means 3 will be coming here. Yes. Okay. Now second row, this element to be made 0. So second row plus first row will make it 0. So we have applied here minus 4, 4 minus 14 added minus 10. Okay, and here also we have applied same operation, 1 plus 0, 1, and that is 1, that is minus 2. Got A will, we should write this A always here, means we are pre-multiplying with corresponding elementary matrix. Next, this element we have to make 0, so that the operation is R3 plus 3 R2. Here also 3 R2 will give us 3 plus 3 6, minus 6 plus 1 minus 7, correct. And here it is 0, 3 times minus 30 plus 20 minus 10, correct. Then this time we are bound to apply fractional operation, because in inverse actually we have seen ultimately inverse is 1 by determinant A into adjoint A. So in fraction always will be coming in the answer. That's why this minus 10 we want to make 1. So minus 1 by 10 multiplied with third row. So this becomes 1, but here fractions coming. So minus 3 by 10, minus 6 by 10 means minus 3 by 5, minus 5 by 10 means minus 5 by minus 10 means it will be half, correct. Now this 1 R1 plus 14 R3, why we want to make this element 0? We want to make this as unit matrix, so this should be made 0. So R1 plus 14 R3, if we do, it will be 0, and R2 change to R2 plus 10 R3, it will be also 0. So this operation we have done, so 0 0 coming, but here accordingly we have changed. Okay, R1 plus 14 R3, so 14 times there, this 14 minus 42, 14 R3 minus 14 R3. So 7 minus 21 by 5 when added with 1 minus 21 by 5, 1 minus 21 by 5. So this calculation will take some time, so it is minus 16 by 5. Okay, you can do other calculations here. Now this minus 6 to be made 0 and this to be made 1. So we have done second row change to 1 minus 1 by 4, second row, R2 change to minus 1 by 4 into R2, so that this becomes 1, and here just minus 1 by 4 multiplied with that, so half 5 by 4 minus 3 by 4, correct. Next this is to be made 0, so we shall add 6 times second row with first row, so R1 plus 6 R2, so this becomes 0 means this left side becomes unit matrix and right side accordingly we have changed. You will see it later. Okay, so this is unit matrix, this is a new matrix, a P equal into A, so I equal to PA, where P is this matrix. Therefore this P is the inverse of A, so A inverse equal to P means this. So this is the process how we find inverse by Gauss-Jordan method. So some fractional operations are essential here, so it takes time. Our usual process 1 by determinant of A into adjoint A is easier rather for this type of examples. Still Gauss-Jordan method for a big matrix, large size matrix, this will be easier comparatively. That's why it is done. So thank you for today.